Thank you very much. And I don't know whether this was by intention or by chance, but I think it's excellent that my talk follows Yael's talk because of the contrast. Whereas she was working with tweezers, we work with a sledgehammer. My talk is on pulsed submerged discharge production of carbon and metal nanoparticles. And basically, this is a group effort, and my job is just to talk. All the rest of them did the work. In particular, the effort is led by Nahum Parkansky from my laboratory. In the literature, there's all kinds of talk about what happens when you reduce the size of bulk material to the nanoscale. There's a lot of talk about that it can significantly increase hardness. It can, let me just get this thing here so we can all see. It can increase the strength and toughness of the material, particularly at low temperature. It can increase super plasticity at high temperatures. It can increase chemical selectivity at surface sites and significantly increase surface energy. I take it for granted that all this is true. I haven't checked. My concern is, how do we make the material? And the technique which I will talk about, we call submerged pulsed arc synthesis of nano and micro-sized particles. And the basic idea is rather simple. We take a container of some fluid, in our work, water or alcohol. We place in there 2 electrodes of some materials. We apply a high voltage pulse, and we produce an electrical discharge. An electrical discharge means the passage of electrical current through a material which is normally an insulator. And this produces a plasma. And I'll show you a movie in just a second. The result is that we produce nano or microparticles composed of some combination of whatever atoms is in the liquid and whatever atoms are in the electrodes. And many of the particles, most of the particles, are small. Now, if I can just turn this off for a second and go to over here and show you a movie. What you see here are the 2 electrodes. This is inside a 1-liter beaker that's about half full with some liquid, probably water. I don't remember, to tell you the truth. And you have to watch this area right here. What we'll do is apply about a 1 kilohertz chain of high voltage pulses, pulse duration less than a microsecond, nanosecond duration. We have another nano here. And here we go. Watch this area right here. You won't miss it when it comes. There we go. Okay? And what we're doing is producing, if you will, a bubble containing plasma. Now, for the sake of the biologists, when our side of the bridge says plasma, what we mean is an ionized gas. Nothing at all to do with blood plasma. But just by the way, there's another biological connection. We use the same process to kill bacteria. If we throw some E. coli in here, after about 5 seconds of treatment, none of them are alive. Okay, now I have to close this. Go back to here. And now continue. Now, what we think is happening is the following. Clearly, we're producing a plasma. You could see it, and I could see it. The plasma is consisting of ionized material that either or both came from the electrodes or from the liquid. In fact, if we look at the spectrum of these discharges, we see characteristic lines of atomic hydrogen, as well as OH, amongst other things. Those are easy to identify. I have to make this thing show up again. Hold on. Come on, visible, visible. Yes. Okay. Now, either during the process or after the end of the pulse, the the condensable part of this material condenses. And it happens at a very fast time scale. During the process, there's an extremely high gradient between temperatures that possibly are around 10,000 degrees, for sure to around 4,000 degrees in the plasma, to basically room temperature in the liquid. And the gradient is very, very small. So I think we have some condensation occurring at this interface, but there's not a lot of time for it to happen. And therefore, the size of the condensates is very small. Now, we actually do this in two modes. What I showed in the little movie was a breakdown mode, in which we applied high voltage between fixed electrodes. It's actually more convenient to work in what we call the contact mode. Basically, we have a vibrator, and don't get your ideas up here. One electrode is connected to a vibrator, and it's contacting the other electrode at a frequency of about 100 hertz. And with every contact, there's a capacitor that's charged. When you make contact, current starts to flow, and the contacts bounce. When they bounce apart, it draws an arc. An arc is a low voltage, high current discharge, and that also produces a plasma. The nice thing about this is that it's cheap. If you talk about, well, every lab can do what Yael was talking about, every high school student can do what we're talking about. $40 in his pocket and a little bit of ingenuity, you can make this apparatus.
Actually, it's an enriching system of an old car.
Yeah, actually, yes. You're right. If you want to go back even further, people were doing these kinds of experiments in the 19th century. This is a oscillogram of the current and voltage through the discharge in the contact mode. This dotted line is the voltage. The capacitor was charged, in this case, to about 75 volts. When contact was made and the arc was drawn, it drops down to the typical arc voltage, in this case of around 20 volts. And it produces a current pulse of about 20 microseconds duration and a peak current of about 120 amperes. This is the voltage waveform from the high voltage generator, which is far more complicated. In this case, the capacitor that was charged was actually tens of meters of coaxial cable that was charged to about 7,000 volts, RG8 if anyone is interested. Well, you can do all kinds of combinations of materials here. First of all, you can vary the materials of the electrodes. They can be metals, metal alloys, they can be carbon. The liquids can be changed. In our work, we use deionized water and various hydrocarbons, mostly ethanol. That way, if the experiment failed, at least you can use the raw material. Other people in the literature have used liquid argon and liquid nitrogen. After you let this process run and then evaporate the liquid, you're left with a powder that can be pure metals, metal oxides, metal carbides, various metal alloys, various kinds of carbon and carbon-containing powders, and carbon-encapsulated metal particles. And what I'm going to do for most of the rest of the talk, until Yael starts waving at me and telling me that I should conclude, is go through basically a zoo of various kinds of particles that we've produced in the lab. For example, if we use contact mode arcing in ethanol from a pair of nickel electrodes, we find floating near the top of our beaker of liquid nanoparticles. I think the scale bar here is 2 nanometers of crystalline nickel, or if the electrodes were tungsten, nanoparticles of crystalline tungsten. If we do the discharge in alcohol, we can form what we call nano onions. I don't know how good this shows up. With a little bit of imagination, you can see these circles. This is sort of like a fullerene inside of a fullerene. Okay, think of a multi-wall carbon nanotube, but spherical. And that's what we have here. The scale bar here is about 5 nanometers. Sometimes these tend to cluster together in a liquid, and you get clusters of these things. We're concerned, being from the Faculty of Engineering, that eventually you want to do this in a factory, and therefore production rate and scalability are things that are important to us. So we've done a lot of work in measuring erosion rate and hence production rate of particles. And depending upon the pulse energy, in other words, how much energy you're storing in the capacitor, and the pulse repetition rate, this will control the erosion rate and therefore the production rate. And the scale here is in milligrams per minute. This was in the contact mode. It was operating at 100 hertz. And, of course, you can see that with the energy of the pulse, the production rate goes up more or less linearly. No big surprises. And engineers don't like big surprises. Physicists love them. When they give a big surprise, there's one of two choices. Either there's some interesting physics. More often, there's a mistake in the experiment. But we don't like surprises. We like things which are nice and linear. This is a case of the contact mode carbon production as well as the total production. In the case of a discharge between nickel electrodes in alcohol. And basically, to determine the carbon production, we take the weight of the powder that's produced, subtract the erosion of the electrodes, and assume that the rest of it is carbon. And again, it's a more or less linear growth with pulse energy. This is an X-ray diffraction pattern of powder that was produced, contact mode between two nickel electrodes operating in alcohol. And the vertical lines show the book diffractogram from pure crystalline nickel. And what we see is that adjacent but displaced from each line is in fact the line that we measure. And there are two things that are significant here. First of all, of course, that the peaks are broadened, and this is characteristic of small crystallites. But the other is the displacement. And we believe that the explanation is that we have a supersaturated solid solution of carbon within the nickel. In other words, far more than the equilibrium solubility enters due to this very fast non-equilibrium process of quenching in I don't even know what time scale. Actually, we can make nice linear formulas to relate the production rate to the various. This is the only, by the way, this is the only equation in the whole talk. You can rest assured. We can relate the production rate to the parameters that we can control, more or less. And basically, it comes down to how much energy do you have to expend in order to evaporate either the electrode material or the liquid material that's used in the discharge. Some more of the same, so I'll just go on ahead. These are some nanoparticles produced with nickel electrodes, contact mode, and ethanol. And perhaps one of the most important things here is that we unfortunately do not get homogeneous particles. We get a distribution of particles. This is the size distribution function as a function of a particle diameter. And what's clear here is that there are many, many more small particles than large particles, and that the distribution function very much depends upon the pulse energy. As we go down in pulse energy, the fraction of smaller particles increases. No big surprise, but it's good to know. This is from all of the particles that we collected after evaporation. You get much more smaller particles if you allow the big particles to settle out, the micron-sized particles, and then work with what's left in suspension. Well, that's also good news, because sedimentation is a cheap process to employ in a factory. The carbon that's collected from running contact mode arc between nickel electrodes in ethanol differs depending upon where you collect it. If we take some of these carbon particles that were floating near the top of the vessel and use XPS, we see that the binding energy seems to be typical of sp2 binding, graphite-like binding. And that's not a big surprise, because this fluorine within a fluorine is basically a graphite-like structure. On the other hand, particles that were collected on the surface of nickel particles, as well as particles that were collected electrostatically, which in a process which I'll describe in a minute, on an electrostatic collector placed in the liquid, had a binding energy which is much closer to sp3, which is diamond-like binding. Now, what this means, I'm not quite sure, but for what it's worth. If you use graphite particles, so that the only material that we're putting into the system is carbon and H2O, in other words, hydrogen and oxygen, then we can get various kinds of what looks to be very poor nanotubes being formed in the liquid. Now, because we have such a zoo of particles, we're looking for every kind of possibility of how to separate one particle from another particle. We mentioned already sedimentation. Gravity is a very cheap method to use. Another possibility is electrostatic separation. What we did is, after all of the arcing, we put in another pair of electrodes and placed a low voltage battery, if you will, between the two electrodes, and observed, first of all, that there is conduction, even though we're talking about alcohol, which is presumably non-conductive. We can measure the current, and particles would collect on these two electrodes, which basically indicates that the particles in suspension carry an electrical charge. And then we looked at the particles that were collected on the electrodes, and they were quite different. In the left case, these were carbon electrodes arced in ethanol, and we can see that the type of particles we collected on the anode and the cathode were very different. One of the interesting ones are these rather square-looking particles collected on the anode. Maybe they're nanodiamonds. Don't know. And these are the type of particles that were produced with carbon electrodes arced in water. Some more pictures. Here's a better picture of these square-looking particles. Some particles which appear to be nanorods or nanotubes of one kind or another, presumably of carbon. If we place zinc electrodes in water, we produce some kind of oxidized zinc residue, which are shown here. This is a composite of some compound of, I won't call it tungsten carbide, it's not stoichiometric, but some combination of tungsten and carbon produced by arcing a tungsten cathode with a carbon anode and ethanol. And these also produce a sort of nano onion, or if you will, fluorine within a fluorine kind of arrangement. These are not graphitic, but rather the characteristic separation is that of tungsten carbide. I think here you can see very definitely this kind of spherical structure. Some of the particles you get are fibrous. Again, some kind of multi-wall nanofiber or nanotube, not quite sure. And now for perhaps the most interesting type of particle we produced. If we take carbon powder produced by breakdown mode arcing between graphite electrodes in ethanol, so basically the only material that's there is carbon. And actually what happened is we had this material and put it on a magnetic stirrer, and before we put the magnet into the beaker, we noticed that the fluid was started to rotate. Couldn't understand what the hell was going on here. So we had the suspicion that maybe some of the particles produced were magnetic, but how could that be? It's just carbon. Well, at any rate, with a little bit of help from Noam Elias, we took this liquid and passed it through what he calls a bioferrograph, which is basically small capillary tubes where you place a strong magnet. And any magnetic particles within the suspension are collected on the wall of these glass capillary tubes. And then we did two things. First of all, we looked at just the particles collected in the raw powder, and there's all different kinds of particles. And second, we took the raw powder because we could get a sizable quantity of it, and sent it to a colleague at the Weizmann Institute, who put it in a magnetic measuring device to measure the magnetic properties of the raw powder. And surprisingly, well, we found that indeed this raw powder of nothing but carbon, in fact, is magnetic. It shows a characteristic similar to ferromagnetic materials. By that I mean it has a saturation region, that high magnetic field. You can kind of see it here, and some degree of hysteresis. And then we looked at the separated magnetic particles from the ferromagnetograph, and we found that there were basically two kinds of particles there. There were agglomerates of more or less spherical particles, and the scale length here is 300 nanometers. So these are nanometric sized particles. This is the scale here. So these are in the range of, 10, 20 nanometers. And some kind of short nanorods or nanotubes. On the other hand, if we look at the residual material, what passed through the ferromagnetograph without being collected, we found all kinds of other shapes and typically larger sizes. The magnetic properties are summarized here. 5 more minutes? Good. We're right on time then. We found that the residual magnetism is around 1 EMU per gram, and just for contrast, iron is about 200 EMU per gram. And this is in the raw powder. In other words, it's all still mixed. What we're trying to do now is collect enough of the pure magnetic particles to determine their characteristics. And just to end with something a little bit more practical, we're trying to upscale this process, not just to produce powder, but also to recycle large hunks of tungsten carbide that are left over from various industrial uses, with the apparatus shown here, which hopefully will be able to upscale to handle tons a day. The idea is to take these big hunks and churn it all into micro and nanoparticles, which then can be used for raw material for sintering, for making, again, big hunks of stuff made out of tungsten carbide. So let me summarize. What I hope we've shown you here is a novel, simple, and cheap method of producing nanoparticles. The powders produced by this method have included pure metals, metal oxides, metal carbides, metal alloys, carbon and carbon-containing powders, and carbon-encapsulated metal particles. We hope that there will be some potential applications to this. In particular, the magnetic nanoparticles of carbon perhaps can be used in medical applications. Perhaps they can be functionalized and then use a magnet to draw them to some particular organ of the body that requires concentrated therapy, and not have a concentrated therapy that could give adverse side effects to the rest of the body. These small particles of carbon perhaps can be used as an additive or as a dry lubricant, as an additive to oils or as a dry lubricant in tribology. We think that the process can be used to crush and recycle tungsten carbide and perhaps some other materials. And we haven't looked into catalysts yet, but that's on our do list in the near future. So I want to thank you for your attention. I think that the short answer is I don't know. It's not something that we looked into. I think an interesting research topic, if anybody wants to try to, let's say, combine a sledgehammer and put it on the end of a pair of tweezers, would be to investigate creating a pulsed discharge at a tip of a nanotube. It's not something that we've done, but I think it would be interesting to do. But I think this will be one of these exasperating experiments which will take a lot of patience and time. So truly my answer is I don't know.
Did you try to analyze the chemical composition of those magnetic carbon particles?
Yes. The best of the resolution of our measuring devices, the only thing we could see was carbon. Now, to be just a little bit more quantitative, of course, the first suspicion that we have, you get interesting physics, there's a mistake in the experiment. And the concern would be that maybe there was some contamination by iron or some other magnetic material. Hydrogen for sure, there must be hydrogen, but I don't think that we would see hydrogen. For sure there's hydrogen. Anytime you have carbon, there's always hydrogen. But what we do know is that there is insignificant amount of, say, iron, which is the most ferromagnetic of the magnetic materials, to give us the magnetic moments that we measured. We'd need at least an order of magnitude more iron than the limit of detection in the, I don't remember whether we were using XPS or SIMS that we were using. So that's not the explanation as far as we know. Now, there's been quite a bit of work recently about magnetic nanoparticles. It's something that's being talked about a lot now. There are two schools of thought. One school of thought is that it's simply defects, which is quite possible. Another school of thought is that in nano-sized particles, because of various symmetry arguments, not just in carbon, also in oxides, there can be a magnetic moment. I don't know, this is, physics, very high physics, beyond my engineer's brain to comprehend, but at least it's being talked about in the literature.
One last question.
In continuation of that question, have you thought of trying to do this kind of experiment in a noble gas instead of water or alcohol, then you would not have that kind of contamination, or no contamination at all. No chemicals.
Well, you'd be only then concerned with what is the purity of your graphite. No, we haven't thought about it, but it's certainly possible. Certainly we could do it in liquid nitrogen. That's cheap. Doing it in liquid argon, that's already a story.
Well, in gas, that's the usual way of producing, this is what everybody does for one month. Okay.